Hi everyone, and welcome back to another project video. In this video I'll be showing my new plank wing RC plane build, which I call the simple plank because it can be built relatively easily with only 1.5 sheets of Dollar Tree foam board. This build took me around 7 hours to complete, and here's a quick parts list. I used my standard set of electronics I use for planes this size, which includes 13-gram Metal Gear servos and a 30-amp ESC paired with a 2205 2300 kV Emax red bottom brushless motor with a 6045 prop. I usually run a 900 or a 1300 mAh 3S LiPo, which supplies more than enough power for unlimited vertical and around 4 to 8 minutes of flight. Every feature on the plane was implemented for a very specific reason. Firstly, I wanted to make a plank wing because I wanted a plane that I could practice inverted and high-speed flying with, occupy very little space, and be very easy to transport on my backpack. I chose to model the custom airfoil off of a PW51 airfoil, as this is a proven shape that is efficient for planks. This was the second time I had experimented with curved bottom airfoils, which offer better stall and flight characteristics than typical flat bottom airfoils, which are easy to make and abundant in the RC aircraft world. I also built in some wing reflex, which essentially creates a turning moment about the wing. The center of lift creates rotation about the center of mass on the plane. Wing reflex therefore counteracts this rotation and helps the plane stay level in the air. On regular wing and tail aircraft, the main wing's airfoil only provides an upward force called lift, and its torque about the center of gravity is counteracted by the tailplane. However, since my wing does not have a tailplane, my airfoil must produce the same effect that a tailplane has. In flying wings, wing reflex can be equated to uptrimming the elevator controls, which changes the neutral position of your controls. However, I chose not to do this, because ideally you'd reserve your trim for the actual flight and not the workbench. I chose a tractor or puller configuration for this plank wing. This means the motor is mounted at the front rather than the back of the plane. Pullers are quieter because, unlike pushers, they do not encounter turbulent airflow from the wing. For me, noise was an important consideration, as I would be flying in parks and other locations that are sensitive to noise. If you're familiar at all with radio control wings, you'll notice that they're 99% pushers because they usually house camera equipment in the nose. However, I wanted as much weight up front as I could possibly manage, as well as the ability to have full span Elevons for increased maneuverability. In flying wings, Elevons act as both the elevator and the aileron, hence the name Elevon, and help the plane to both pitch and roll. Larger Elevons mean that the wing can be more responsive in flight because they deflect larger amounts of air and therefore generate larger forces. You may be wondering why I decided to go with 2 vertical stabilizers. Since there are 2, there is less consequence of misalignment of one of the fins when building the plane. In addition, the fins don't block the rubber band slit on the back between the Elevons, which is used to mount the wing to my backpack. And I angled the fins at roughly a 15-degree angle. On many military aircraft such as the FA-18 Hornet or the SR-71 Blackbird, both of which often encounter high angles of attack upon landing, the forward body of the plane can produce vortices of air that flow either into the center of the plane or outward. This test footage, courtesy of NASA Langley, shows the vortex created by the F-18's nose and cockpit area and how it flows outward away from the center of the plane. The vertical stabilizers on the F-18 are therefore canted outward to intercept the vortex, ensuring sufficient airflow around the rudder and therefore good yaw authority, which is important for stable flight. Stealth fighters, such as the F-35, also employ stabilizer canting to reduce their radar signature. But I'm not worried about showing up on a potential enemy's radar. And since the wing of my plane has the same airfoil along the span, and since there wouldn't be anything to affect the airflow ahead of the stabilizers, the whole wing would probably not produce any significant vortices around where the stabilizers are located. The whole wing would probably stall at once, and so any angle of cant would not affect the aerodynamic properties. But I implemented the cant anyway because it looks pretty cool. Lastly, the CG, or center of gravity, on planks is very particular and therefore difficult to get correct. As with all aircraft, the center of gravity must always be ahead of the center of lift of the wing, so the plane can remain stable in the air, similar to how a wind vane works. On a wing of this size, the range of possible locations can span around only an inch according to this CG calculator. It recommends a minimum of 1.2 inches back from the leading edge, and a maximum of 2 inches. Experimentally, however, I found that the range was closer to 0.7 to 1.5 inches. This is probably due to the fact that I prefer slightly nose-heavy planes for stability at high speeds, and because the CG calculator was very simplified and did not take into account the specific airfoil I used. For the Maiden flight, I guessed the best location and luckily it went off without a hitch. And now I'll leave you with some footage of the second ever flight of the swing.
Alright, ready?
Yeah.
And that's it. Thanks for watching, and if you have any questions, feel free to leave them in the comments below.